Hi, hello everyone. Welcome you all for the post-contest discussion of Codechef Starters round 145. So let's start with the discussion. So the first question is make my array equal. The name of the question is make my array equal. Let's go through the problem statement. You are given an array A of length n. Determine if it is possible to make all the elements of A equal by performing the following operation any number of times. That is, what are the operations that you can perform? You can choose two distinct indices I and j such that is you are choosing two distinct indices, that is I is not equals to j, and update the value at index I by setting ai to ai plus aj. For example, if you have this array and you choose I equals to 5 and j equals to 3, in that case you are going to replace a5, that is AI, with A5 plus A3, that is AI plus AJ. This is the operation you can perform. So you need to output yes if it is possible for you to make all the elements of the array equal after performing several, possibly zero of these operations. Otherwise, you need to output no. Okay. So you are given number of test cases, the single integer n, that is the length of the array, and the numbers of the array as well. Okay. So how to think of this question? How we can do this? So first of all, let's understand the question once more. In the question, you are given an array A. You have an array that basically contains n integers. Okay. Now what you can do is you can select any two indices. That is, you select these two index, and in any of these index, you can write, like if let's suppose you select this as I and this as j. So you can replace the value of this ai to be equals to ai plus aj. And if you let's suppose select this as I and this as j, then again this is also valid. So now this element will be replaced by the sum of these two elements. And what is your aim? Your aim is to make all elements equal. This is your aim. Okay. Now the question is, can you do that or not? Can you make all elements equal or not? So how to think of it? Okay. So just think that you have made all the elements of array equal. Okay. And you are left out with only one element. You are left out with only one element that is not yet equal. Let's suppose you are going to make all the elements of array equal to x. So let's suppose this value is x. This all have become x. And there is only one value that is not yet equal to x. So now what will be your aim? Your aim will be to make this value x as well. And you will see that if that is possible or not. So in that case, what you will do? In this particular index, what is the value that you can write? At this particular index, the value that you can write is y plus x. Because if you select this index as I, the options for selecting index j is any of these. And at all these indices, the value is x. So what is the value that you are going to write at this y? The value that you are going to write at this particular index I is y plus x. Now, when will y plus x be equal to x? When will it happen? It will happen only when y is equals to 0. This x gets cancelled, so y is equals to 0. So from this, what is the conclusion we made? We made a conclusion that we can make each and every element of the array equal only when it contains at most one unique positive integer. That is, if array is something like this, like 0, 6, 0, 0, 6, 0, 6, now you can make this all elements equal by replacing all these values by the sum of these indices. Like 6 plus 0, this will be replaced by 6, 6 plus 0 will be replaced by 6, and like this. But if you have two distinct positive numbers in the array, like 1, 2, then at any cost, you can't make all the elements of the array equal. And what was the reason? The reason is because at the end, when you try to make the unequal element, at the end, when you try to make the unequal element equal to the equal element, in that case, you need to add some values over here. So this value should be 0. This value should be 0. So you can never make all the elements of the array equal at a single time if it contains two unique positive integers. So if it contains at most one unique positive integer, that is, the array can be something like this as well, all zeros. So it is equal only, isn't it? So what we end for? We conclude that if the array contains at most one unique positive integer, in that case, our answer will be yes. Otherwise, our answer will be no. So that's the approach for this question. Let's jump on to the code. Just a minute. Yeah. So implementation depends on you, how you want to code it down. The logic remains the same. You only need to check that how many distinct positive integers the array contains. So took the input of n, took the input of vector, that is all the elements of the array, constructed a map, initialized my count to 0. This count basically tells me how many unique positive integers I have. Then I went to each and every element of the vector. If the element is not equals to 0 and mp.find it is equals to mp.n, that is, this particular element is still not inserted in the map. So what we do, we insert that particular element, and since we know that we have found one unique positive integer, so in that case, simply incremented the count. At the end, if my count is lesser than equals to 1, that is, I know that I can have at most one unique positive integer, right? So if my count is lesser than equals to 1, in that case, I am printing yes, else I am printing no. So this is the code and the logic for the first question. So let's jump on to the second question. Wait a minute. Yeah. So the name of the question is Make Bob Win. So Alice and Bob are playing a game. They have with them a binary string S. Alice and Bob alternate making moves with Alice going first. Okay. On their turn, a player does the following. Choose a non-empty contiguous substring of S, all of whose characters are the same, and delete it from S and concatenate the remaining parts. Okay. So Alice wins immediately when S does not contain any occurrence of 1, while Bob wins immediately when S does not contain any occurrence of 0, and both players will play to win. So just note down that if the string initially does not contain any occurrence of 0, so Bob automatically wins. Because for Bob, the winning condition is when the string does not contain any occurrence of 0. So Bob wants to win the game. So before the game starts, he can flip some characters of S. So you need to find out what is the minimum number of flips Bob needs to make to ensure that he can win. Okay. So let's understand what the question says. The question says that you have some binary string, something like this. If you have something like this binary string, you have a string something like this, and there are two players, Alice and Bob. Now what they will do is, what a person can do is, a person can remove all the elements in the substring. A person can remove all the elements in the substring if the elements in the substring are equal. That is, if I am, let's suppose, Alice, I can remove any of these elements. I can remove the entire this substring, or I can remove this substring, this substring, this substring, this substring, since all the elements are equal, and this substring as well. So these are the options I have. So I can remove any of the substring. And similarly, the Bob can do that as well. Now they are playing the game with alternate moves, with Alice starting first. And Alice wins the game if there is no occurrence of 1 in the string left. And Bob wins the game if there is no occurrence of 0 left in the string. Now for you, they have made a question that they love Bob. They want Bob to win the game. So for Bob to win the game, they ask you that how many bits over here in this particular question you should flip so that the Bob wins the game. how many bits you need to flip so that Bob wins the game definitely. There is no chance for Alice. Okay, so this is the question. So how to solve this? So since you know that, okay, we will have something like this now, that if Alice wants that there is no occurrence of one, so in every of his move, what he will do? He will remove one from the string, isn't it? He will select one substring that contains one, and he will remove that entire substring. Similarly, since Bob wants there should not be any occurrence of zero left, so in his move, what he will do? He will select a substring and remove all zeros from it, isn't it? Okay. So I know that Alice is starting first. Okay. So since I have something like this, that I am removing all the continuous characters, so what I will have? I will have some occurrences of zero, then some occurrences of one, then some occurrence of zero, then some occurrence of one, then some occurrence of zero, and something like this. It may either end with either zero or one, isn't it? And it can start from 0 and 1 as well. It can start from any of the characters, will end at any of the characters, and there will be something like this, alternating pairs of subsequent, like same characters in the string. You will have some zeros, then some ones, then some zeros, then some ones, then some zeros, something like this. And if I am a person that, let's suppose, I don't want one to occur in the string, so when I am selecting a substring, I will remove all its characters, isn't it? I will not do something like this, that I remove half characters of this one. What I don't want any one in the string, no? So I will remove this entire set of characters. Okay. Now, if you observe, if you observe and think a bit, you will be able to come down to the conclusion that, okay, if I have something like this, that I am starting with one, that is, I have some ones at the start, then I will definitely have some zeros, then I will have some ones, then I have some zeros, and I end at one as well, and I end at one as well. So if this is the case, and since Alice is starting first, so what will Alice do? Will Alice select this substring and remove all ones, or he will select this particular substring or this particular substring? Yeah, definitely. He will select this substring or this substring only. No, he will not select this as first, because if he does so, then you will get all zeros together. Bob will remove these zeros and the game is over for Alice. So what he will do? Let's suppose he removes this substring completely. So now what Bob will do? Definitely, via the same logic, Bob will also not remove this particular substring and remove all the zeros from this particular substring, isn't it? So this also gets removed. Now Alice has only two options. And whatever option he chooses, this substring or this substring, after that, Bob has the option to choose this entire sets of zero, remove it, and win the game. Isn't it? So, what we infer from this? We infer that if we start with the one and end with the one, in that case, there is always a win-to-win situation for Bob. Else, if this is not the case, that we are, let's suppose, starting with one and ending with zero. We are starting with one and ending with zero. So now tell me, who will win the game? The first move is with Alice, right? So what Alice will do? Alice will remove this particular substring. Then Bob will remove any of these substrings. Let's suppose he removed this substring. And then Alice has the option to remove this particular substring and win the game. So if we have, the same can be, the vice versa can be said for this as well. That if we are starting with zero but ending with one. So the case remains the same. Alice first of all removes this particular substring. Then Bob removes this. And now Alice removes this and wins the game. So if we are either starting with one and not ending with one, or we are ending with one but not starting with one, in that case, Alice will always win the game. And let's see the last possibility. The last possibility is that we start with zero and end with zero. This is the case for the last possibility. So now if you try to perform operations, so Alice will, let's suppose, remove this particular substring. Then Bob will remove this entire substring, because now they will concatenate. You will have continuous zeros. So Bob will remove this particular substring. And now Alice will remove this particular substring and win the game. So what we observe? We observe that Bob will win the game only when we start with 1 and end with 1. So at max, just tell me, if you have a string, at max, how many characters do Bob need to split? Bob needs to flip. So at max, he needs to flip 2 characters, because at max what we can have, we are starting with 0 as well as ending with 0. So in that case, Bob needs to flip both of these characters. If he is able to do so, then he will have something like this, that the string is starting with 1 and as well as ending with 1. So in that case, Bob will definitely win the game. And if let's suppose we have something like this, that it is starting with 1 but is ending with 0, in that case, Bob needs to flip only 1 character. That is the one that was 0. He needs to flip only this particular character. And if we have a string that is starting with 1 as well as ending with 1, in this case, Bob does not need to flip any of the characters. So this was the question for you. This was the logic actually. So let's see the code. So took the inputs of length of the string, then took the input of string. Now, if the value of n is 1, I handle this case exclusively, that if the value of n is 1, so if the character of the string is 1, in that case, Bob does not need to perform any operation, else he need to perform one operation. Now, initialized my temp to 2. Temp is the maximum number of flips that Bob needs to make. Now, if the first character of the string is 1, so I simply decremented my temp, because now I know that if the first character is 1, I don't need to flip the first character. So decremented my temp. Similarly, if the last character is 1, I again decremented my temp. I know that I don't need to flip that particular character as well. So at the end, I simply printed temp. That is, this is a minimum number of bits that Bob needs to flip to win the game. So this was the logic behind this particular question. So let's move on to the third question. Okay. So this was an interesting one actually. This was actually a completely mathematical based question. If you just write down the things that you need to do, the things will become crystal clear. And once you write it down and just solve 2 to 3 lines, then actually the code for this question is actually very, very easy. So the all thing lies that what you do in pen and paper. So let's discuss it. So name of the question is square string. So the squing value for the binary string s of length n is calculated as follows. Let x equals to 0 be the initial squing value. And for each item I from 1 to n, let j be the largest index such that j is lesser than I and sj is not equals to si. If such an index j exists, then you need to simply add I minus j square to x, otherwise do nothing. Okay. So for example, if you consider this, so for I equals to 1, 2, 3, for I equals to 1, 2, 3, there exists no index j. See, j lies towards the left of I, that is j is lesser than I. So there does not exist any index j for any of these indexes to the left of these particular indexes for which the characters are not equal. So they will contribute nothing for the squing value. Similarly, for I equals to 4, we have 3 possible j values, isn't it? So the squing value will be 4 minus 3 square. There are 3 possible j's values, isn't it? But now if you look up to the question, for each I, you need to select the j that is the largest index such that sj is not equals to si. So for this particular I, just tell me which value of j will you select. This particular value, right? Because this is the largest value of these possible 3 indexes for which the value of the character is not equals to this particular character. So what will be the squing value? Squing value will be 4 minus 3 square. Similarly, for this particular character, the largest index such that sj is not equals to 1, that is this particular character, will be 3. So 5 minus 3 square. Similarly, for this particular character, the largest index such that the values are not equal is this particular index 1. So 6 minus 5 square. So the total squing value will be 1 plus 4 plus 1, that is 6. So now, what is the question? This is actually how we are calculating the squing value. But the question is that you are given n. So we know that if we are constructing a binary string of length n, so there are total of 2 power n binary strings possible, isn't it? So you need to find the sum of all their squing values. And since this sum can be large, so you need to compute it modulo 1e9 plus 7. Okay. So that's the question for you. A simple input, you are taking n as input. You know that there will be 2 power n possible binary strings because at every character you have two options. Either you select 0 or 1. So this leads you to 2 power n binary string. So you need to tell that for all these binary strings, what is the summation of squing values? So that's the question. I hope the question is simple and understandable. Okay. So how to approach this? So what I thought during the contest was that, okay, let's think index wise. I know that in this question, since we are calculating the since we are calculating the differences, so okay, so let's consider that, okay, this is index 1, this is index 2, 3, 4, this is some index I, okay, 5, 6, 7, 8, 9. In total, you have 9 elements. So if I am talking that, okay, how many, what is the total summation of squing values in which my value of I is this particular index? See, over here we have two indexes, right? I and J. So I is the element index towards the right and J is the element towards the left, index towards the left. So if this is my I, so what is the summation of total squing values I will get, considering all the possible substrate? So see, what are the options I have? At this particular index I, my value can either be 1 or 0. Okay. So whatever answer, first of all, you need to understand that these values are symmetric. Whatever answer I get for 1, the same answer I will get for 0 as well. If you are not getting this, you will get it in approximately 5 minutes. Let's start with this ith character as 1. Okay. Let's suppose we have this ith character as 1. Okay. Now, this particular character, what will be the squing value? What are the possible options? The possible options are what we will do for the squing values. For squing values, we need to look for the largest j out of these possible j's. We need to look for the largest j for which sj is not equals to 1. So for that, what you can do? The largest possible option is you will get 4. So this value is, let's suppose, 0. If this is the case, so what will be the contribution of squing value? The contribution of squing value will be, okay, wait, let me correct these indexes. If this is 1, this is 2, this is 3, this is 4, this is something like 5. I have just initialized it with I. Then this will be 6, 7, 8, 9, 10. So in total, you have 10 elements. Okay. So if let's suppose this is index I, the value at index I is 1. So what are the possibilities? If this particular index is 0, so what is the squing value with this I as with this ith index as 1? The squing value is I minus 4 square, isn't it? Multiplied by, now I don't care what actually are present in these spaces. I don't actually care that. Do I care? Do I care that what actually are present at this particular indexes? Will my the squing value change? No, no. Because for this, if this is 1, this is 0, whatever substring I have, for this particular I will always get j as this particular index only. So if let's suppose, so how many characters do we have over here? If you just notice, since we are considering one-based indexing, we have I minus 2 characters, if you notice. So we have total of I minus 2 characters. And similarly over here, how many characters we have? if we have in total n elements, so the number of characters that we have towards the right is n minus I. So can I say that this string value will be there for how many strings? It will be there for I minus 4. So if I, let's suppose, just take this value as 5 for now, okay? Just initialize with it so that you all understand better. So if I just calculate I minus 4, so it is nothing but 5 minus 4 square. So the value will be 5 minus 4 square, which is 1 square multiplied by 2 power I minus 2 multiplied by 2 power n minus I. This will be the total summation value, isn't it? Isn't it? Okay. Similarly, with this value I as 1, if I have 1 over here, if I, let's suppose, have 1 over here, and then I have 0 over here, that is, what are the possible values of j with this as I? My j can be this, this, and this. So we will add all the possible values. So first of all, I assume this as my j. If this is j, so this character should be 0. Now, if I am assuming this is my j, so this value should be definitely 1. That is equal to the character present at this particular position, isn't it? So with this as j, just tell me what will be the total swing value. The total swing value will be 2 square. That is the difference of 5 minus 3, 2 square, multiplied by 2 power I minus 3, multiplied by 2 power n minus I. Because now over here we have I minus 3 characters in the left. So whatever these characters I don't actually care. So it is 2 power I minus 3. Similarly, towards the right, what is the combination? I don't care. So 2 power n minus 1. And the difference is 2 square. So this is the total swing value. Similarly, with j as 2, can I say with j as 2, my swing value will be 3 square multiplied by 2 power I minus 4 multiplied by 2 power n minus I. Can I say this? Can I say this? So can I write? And similarly, if I write for j equals to 4, with j equals to 1, so my swing value will be 4 square multiplied by 2 power I minus 5 multiplied by 2 power n minus I. And now if you notice, with value of I as 5, this value becomes 0. So from here, I drew the conclusion that, okay, for any index I, the total swing value will be, wait a minute, just let me tell this thing also, that whatever value we did with this value as 1, with this ith value as 1, the same answer we will get with this value as 0 as well. So if you observe, if you add all these values, just see 2 power n minus I term is common. So if you just simply take 2 power n minus I term as common, and you know that whatever value you got for 1, the same value you will get for 0 as well. So multiply simply 2 over here for that thing. And once you take 2 power n minus I common, what is the value that you will get? You will get 2 power I minus 2 multiplied by 1 square plus 2 power I minus 3 multiplied by 2 square plus dot dot up till 2 power 0 multiplied by I minus 1 square. Because if you look for the last j, what will be the difference? The difference will be I minus 1 for the last j, isn't it? And what are the number of characters towards the left? 0. So 2 power 0. That's the reason we will go till 2 power 0 I minus 1 square. Now if you simply take 2 power n minus I inside, you will get 2 multiplied by, wait a minute, yeah. So 2 multiplied by 2 power n minus 2 into 1 square plus 2 power n minus 3 into 2 square plus dot dot up till 2 power n minus I into I square. You will get this now. If you take 2 power n minus I inside, just a simple mathematical conclusion. I simply took 2 power n minus I inside. Okay. So what do we draw a conclusion from here? Like these are for every I. We need to add it for every I. With I starting from 2 to n. We need to add this for every I. Because I will start from 2 only. Now, then only we will get some characters towards the left. If we start with 1, we will not get any characters towards the left, isn't it? So if I simply write it down again, let me write it down again. What is the final we got? The final we got 2 multiplied by, for any index I, the total squaring value will be 2 power n minus 2 into 1 square plus 2 power n minus 3 into 2 square plus dot 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 up till 2 power n minus I into I minus 1 square. This is the value we got. Okay. So what do we infer from this? If I, let's suppose, just write it for some I. Let's suppose I write what will be the answer for I equals to 2. So the answer for I equals to 2 will be, let's suppose we have the value of n as 4. Okay. We are not putting the values, but what are the possible values of I? The values of I are 2, 3, and 4. These are the possible values of I. So let's write for I equals to 2. For I equals to 2, the total squaring value will be 2 power n minus 2 multiplied by 1 square till I equals to 2. So since over here we have I as 2, so we will only get this particular term. Similarly, for I equals to 3, what is the value we will get? We will get 2 multiplied by 2 power n minus 2 into 1 square plus 2 power n minus 3 into 2 square. Similarly, for I equals to 4, what? For I equals to 4, what we will get? 2 multiplied by 2 power n minus 2 into 1 square plus 2 power n minus 3 into 2 square plus 2 power n minus 4 into 3 square. This is the value we will get. So if I add all these values, are you able to observe one thing? This particular term comes n minus 1 time. This particular term comes n minus 1 times. Similarly, this particular term comes n minus 2 times. See, it came over here and it came over here. Similarly, the next term came n minus 3 times. Isn't it? So this is the pattern. So what actually you need to calculate? If you just observe over here, you need to simply calculate summation of 2 power n minus I multiplied by I minus 1 square multiplied by how many terms, how many times these terms are coming? These terms are coming n minus I plus 1 times. That is, if the value of I is 2, how many times we got this term? N minus 1 times, isn't it? N minus 1 times, that is 3 times. So that value will be nothing but n minus 2 plus 1. That is n minus 1. So every term 2 power n minus I is coming n minus I plus 1 time. So we need to simply calculate this value with I ranging from 2 till n. So that is the simple thing that you need to calculate. Summation of 2 power n minus I multiplied by I minus 1 square multiplied by n minus I plus 1 with I ranging from 2 to n. If you are able to calculate this thing, then the things are done. And how we were able to reach till here? We simply wrote what we need to do. We first of all considered with every index what is the possible squaring value we can get, and then for every I we simply added that, and then we observed the pattern that okay, this particular term is coming n minus 1 time, this is n minus 2 times, and so on. And then we simply formed this summation equation which led us to this formula. So now this can be easily calculated, isn't it? This can be easily calculated. So let's jump onto the code. Okay. So initialized, took the value of input n, initialized my answer to 0. Now went for every I from 2 to n, initialized my temp to 1. First of all, I calculated 2 power n minus I. Okay, here are 3 terms. 2 power n minus I minus 1 square, and n minus I plus 1. All needs to be multiplied. So first of all, in my temp, I multiply 2 power n minus 1 by taking mod into consideration. So I already have this expo function defined in my template. So if you look, this is the expo function which calculates a power b taking mod in consideration. So this is something that you all, I expect that you all know this, how we can calculate a power b by the help of like iteration approach, like dividing them into 2, divide and conquer. I hope that is clear. If not, you can read any of the article how you can calculate a power b and taking mod into consideration. So first of all, we calculate 2 power n minus I, multiply it with temp, and simply took the mod. Then we need to calculate I minus 1 square. That is, need to multiply temp with I minus 1 square. So multiplied temp with I minus 1 first, took the mod, then again multiplied it with I minus 1, took the mod. So now my temp gets multiplied by I minus 1 square. Now the third term that we need to multiply is n minus I plus 1. So simply multiplied n minus I plus 1, took the mod, added the temp to my answer. For this particular I, this is the answer, and simply took the mod. At the end, we know, just don't forget this term. I left out it over here. Wait a minute. This 2 was left out. So 2 multiplied by this value. We are getting this 2 now. We took 2 as common and added these things. So this 2 was left out. So 2 multiplied by what answer we get. So actually, this is the answer. So simply multiply 2 to my answer, took the mod, and printed the answer. So this was the explanation for the third question. It was actually more very much on the mathematical side, and if you just write down the equation and solve it with like till 2 to 3 lines, you will definitely be able to generate these type of equations. And once you generate this, the code is super easy. There is nothing rocket science in the code, but to reach till here, you need to be brave and write 2 to 3 lines at least, so that the things become clear that what actually is happening. Because by just looking at the question, you will not be able to reach to this particular expression, right? You need to reach here somehow, like by writing it down in pen and copy and solving 2 to 3 lines. Yeah. So this was the third question. So let's jump on to the fourth question for the day. And it was actually, if I want to talk about this question, then this question was actually something that was written to confuse you all very much. But in actual, this question is not so tough. Like, it's easy. It's not so tough. So let's see how we can solve this. So yes, the name of the question is beautiful array. So chef has an array A of length n. He defines the beauty of the array to be the bitwise and of all the numbers in the array. That is, if he has n integers, then the beauty of the array is a1 and a2 and up till an. So chef asks you to answer q queries on this array. In each query, you are given two integers x and k. So at most k times, you can do the following operation. That is, choose two integers L and R. Then for each index from L to R, you can replace AI with AI XOR X. So here XOR defines the bitwise XOR operation. So the answer to the query is the maximum possible beauty of the array A after performing the given operation at most k times. That is, this is one operation. You are choosing a substring from L to R and doing the XOR operation of every number in the substring L to R with X. So you know that this array does not actually change it. That is, for every query, you have the original array with you. So for every query, you need to answer originally. So you need to tell that for every query, what is the maximum possible beauty of the array A that you can produce. So what is the question? The question is that you have an array A with n integers, and you, for every query, you are given two integers k and x. K is the maximum number of times you can perform the operation, and x is the value with which you will XOR the elements of the array. Now, what you can do is in one operation, you will choose a substring. Let's suppose I choose this particular substring. Then I choose this as L and this as R. I choose this particular subsequence. Then what I will do is I will go to each and every element of this array and simply XOR with X. So if let's suppose this is A2, A3, A4. So now A2 will become A2 XOR X, A3 will become A3 XOR X, and A4 will become A4 XOR X. So this is something that you can do with each and every operation. So now you need to tell that what is the maximum value of AND that you can produce. That is, at the end, what you are going to do, you are going to calculate the AND of all the values in this array. And then you need to look for that what is the maximum AND value that you can produce. So this is the question for you. So how to think of this question? See, it's not actually so tough. Wait a minute. Yeah. So Okay, what I am doing? I am doing an AND operation with X, sorry, XOR operation with X, and then calculating the final AND value. So how to think of this question? So the first thought that comes to every one of us mind that, okay, we are talking of AND operation. So for any ith bit, for the AND value to be 1, what is the necessity that we have? The necessity is that all the values at that particular bit position should be 1. I am talking of the ith bit as of now. Okay. I don't care what bits are present in this number in the left and right hand side. I am talking of the ith bit. So for the ith bit, for the final AND value to be 1 for this particular bit, so what I should have? I should have all values at 1. Okay. So now, if I am aiming something like this, that I have the 1 as a result as the ith bit, so I may have cases like this. In first two numbers, I have 1. Oh, let's not take this. For first number, in this particular ith bit, I have value as 1. For the second number, I have 0. For the third one number, I have 1. For the fourth and fifth number, I have 0. And for the fifth number, I have 1 again. Now I know that if I am doing it the AND operation, I will not get 1 over here. I will definitely not get 1 over here. Okay. But if I let's suppose for this particular bit, the value of X is 1. If the value of X is 1, what we know is if we are doing the XOR operation, so which bit flips the bit? The value of the bit should be 1 for flipping the bit. That is, if whatever bit we have over here, if we XOR it with 1, the bit gets flipped, isn't it? If we XOR it with 1, the bit gets flipped. And what we need? We need that the numbers that have 0 value at this particular bit position should be turned to 1. So by looking at this particular bit, if I just tell you this thing that for this particular bit, the value of X is 1, that is for in this particular bit position, the value has bit 1, and this is a configuration of the numbers for this ith bit. That is, the first number has bit 1, the second has 0, the third has 1, the fourth and fifth has 0, and the sixth one has 1. So just tell me the minimum number of operations you will need to turn this particular bit 1 in the final AND operation. What is the minimum number of operations you will need? So the minimum number of operations you will need is 2. Because first of all, you will select a substring and you will select L equals to 2, R equals to 2 and XOR this particular number. Then you will select L equals to 3 and R equals to 4 and XOR these two numbers with X. So when I am doing the XOR operation, just keep in mind the entire number gets XOR. Okay. So whatever bits are present in this position will also change. But yeah, for now, my aim was that I want to turn this ith bit on. So I just see that what is the minimum number of operations I need to turn this particular ith bit on. And and one of the interesting thing for this question is that just observe one thing. It is going to be interesting. That if I am doing the XOR operation, that I apply the operation with this particular value at this particular bit, if I apply the operation, so what will happen? This bit will also turn 1, this will turn 1, this will turn 1. Now, for any other bit, I can't XOR the numbers with X again. I can't do something like this. Now, for any of the numbers, if I now XOR any of the numbers with X, this bits will again turn 0. This bits will again turn 0, isn't it? If I just XOR with X, any of these numbers, this bits will again turn 0, and my aim to turn this particular bit on will be failed. So from this, we draw the conclusion that if we are doing XOR operation in any of the numbers, that will be for only for any one bit. We can aim for any one particular bit. We can't aim for multiple bits. Now, if we get the conclusion that we are aiming for only a single bit, then which bit should it be? So what is our aim? Our aim is to produce maximum AND, isn't it? So which bit should we aim for? We should aim for the leftmost possible bit. that whichever leftmost possible bit can be turned on, let's turn that particular bit on. Okay, fine. So, okay, we got to a conclusion that, okay, we will look for the leftmost possible bit. So what we need to calculate? For every bit, we need to calculate that what is the minimum number of operations needed. And how we can do that? We can just check how many substrings with continuous zeros are present. Like this is one with continuous zero, this is one with continuous zero, and so on. Okay. Now, if this is clear, just look what we will have. Just let me go through some examples. If we have, let's suppose 0, 1, 0, 0, 1, 0, these are the numbers. Okay, this is the first number. This is the uh, configuration of that particular number. Okay, then we have, let's suppose, hmm, yeah, 0, 0, 0, 0, 0, 1. Okay, then we have, hmm, let's suppose 0, 0, 0, 0, sorry, 1, 0, 1. Okay, and then we have 1, 1, 1, 0, 1, 0. Then we have, let's take this as 0 as well. And then we have 1, 0, 1, 0, 0, 1. Okay. Now, if I tell you that my aim is for this particular bit, I want to make this particular bit set. Just forget what are present in the left. Just assume that I want to make this particular bit set. Yeah, let me change this a bit. Otherwise, it will create confusion. 0, 1, 0, 1, 0. Now, if I tell you that I have the value as k as 2 and my value of x is 1, 1, 0, 0, 1, 0. This is my x, this is my k. Just tell me the maximum x that I can produce. So what I will do, I will just go from left to right and just see. So for this particular bit, if you observe, for this particular bit, the number of operations needed are 3 because there are 3 unique sets of substrings of 0, isn't it? So for this particular bit, I will require 3 operations, but I know that since I have only 2 operations, so I would not be able to make this particular bit 1 in the final line. So the result will be 0 in the final line. Okay. Now I go to this particular bit. For this particular bit, I observe that, okay, the value of x is also 1. Only if the value of bit in x is 1, only then only we can turn 0 to 1, isn't it? Otherwise, we can't turn 0 to 1. So if the value of bit at this particular position for x is 1, so we will see how many operations, how many max operations we need to turn this particular bit 1 for all the numbers. So if you observe, we will need 2 operations, isn't it? There are 2 sets of 0. Okay. So what we will do? We will XOR these 3 numbers. We will XOR these 3 numbers with x, isn't it? Now just observe. This is our x. This is our x. And this was the initial AND that we were having. And we know that since we are able to turn bit on for this particular bit for all the numbers, the final AND value for this particular bit will become 1. For this particular bit, it will still remain 0. For this particular bit, it will still remain 0. But if you observe, then, wait a minute, take this as 1. Yeah, take this as 1. Yeah. So if you observe now, then if I am doing XOR of these 3 numbers, if I am doing XOR of these 3 numbers, then since the value of this particular bit for x is 1, what it will do? It will turn this to 1. It will turn this to 1. It will turn this to 1. And what will happen? Something that will happen is that this particular bit will also get turned on accidentally. This was not intentional, but it happened accidentally. And when will it happen? When will it happen? When whatever bit set that you have over here, like over here, if you see the configuration, you have 1, 0, 0, 1, 0. for 5 numbers for this particular bit. And the value of x also was 1. Similarly, for this particular bit position, the value of x was 1. And this was the configuration for the numbers 1, 0, 0, 1, 0. The configuration was same. And if this is so accidentally this bit will also get turned on, where intentionally when we try to turn this particular bit on. So if you are doing XOR of these three numbers with x, so accidentally this particular bit position will also become 1 in final AND operation. So this is something that you need to keep in mind, that if you are doing the XOR operation of any of the numbers, so if you are, let's suppose, doing this for ith bit, so it is not that only for this ith bit the final AND value will get changed to 1. It can get changed for 1 as well. It can get changed for uh, any other bit as well, accidentally, not intentionally. So that thing you need to keep in mind when you are printing the answer. Okay. And now the last thing. The last thing that I need to talk about is that if you have numbers something like this, okay. If you have numbers something like this, so just observe that it may be that for x, this value is 1. The x given to you is, this value is 1. This value is, let's suppose, 1 again, and this value is 0. And the value of k given to you is 2. So if you are getting all ones before only, and the value of x as 1, you don't need to do any XOR operation. Why? Because what is our aim? Our aim is to make the leftmost bit and value as 1. This is our aim, right? So if we just skip this thing, that we don't do XOR over here, but do XOR with this particular number for some numbers, like let's suppose I do it for this, I do it for this. So accidentally, what will happen? Accidentally, this particular bit will get turned to 0, since the bit position in x for this particular bit was 1, and for this particular bit it will turn to 0, and the final AND value for this particular bit will come down to 0. So if we were trying to make the final AND value for this particular bit 1, so accidentally what happened? This particular bit got turned to 0. So we need to keep care of these cases as well, that if let's suppose we already have AND values as 1, and in x for that particular bit we have value as 1, so we know that we can't do any XOR operations, because if we do, then the bits will get turned off and the final AND value will come down to 0 for that particular bit. That is something we don't want. So that is the aim for this question, that we simply move from left to right. So now if I summarize the approach, so what will be our aim? Our aim will be that we will move from left to right if a particular bit, if ith bit is set in number x. So I will just simply look that for turning that bit on in all numbers, what is the minimum operations I need if this minimum operations is, let's suppose, x, and if is let's suppose required, and if let's suppose this required is lesser than equals to k, then we will turn this particular bit on. But what we learned that intentionally when we try to turn this particular bit on, so there can be some other bits that will get turned on accidentally. That is a profit to us, but yeah, that happened accidentally. That was not intentionally, right? So for that, we need to keep a check that what other bit positions are there that have the same configuration like this as this particular bit. So if there exists some bit positions like that, and in X that particular bit position is 1, then we will simply turn that particular bit as on as well in our final answer. So that is the logic for this question. So let's jump on to the code. The code might seem a bit complicated to you all, but this is actually what I have. This is actually what I coded during the contest. So wait a minute. Yes. So first of all, took input of number of numbers and the number of queries. then constructed a vector of size n and took all the values as input. Then to check for a particular bit position, that how many number of, what is the minimum number of operations I need for 0, what I did is I did something like this, that okay, if I have 1 1 0 0 1 1 0 0, so I constructed a vector of size 21, and for this ith bit in my 0th index, I will store that how many the minimum number of operations I need to turn all zeros to 1. So you can see I need 2 operations, right? So this value will be 2, and this value will again be 2, because the number of continuous ones that I have is also 2. So these both values will be 2. So this is something that I am storing in this uh, A vector. Okay, so constructed a vector A of size 21 cross 2. And if I just let you all know the code of this one. So this is actually the code for this one, that I am going over all the indexes, initializing my j to 0, while the value of j is less than n. If a particular, if the particular ith bit is set in this particular number, so I will just see that how many continuous numbers are there for which this particular bit is set. So I will simply increment that. I will keep on incrementing my j, and those numbers as a whole will contribute to 1, isn't it? This whole numbers as a whole contribute 1. These whole numbers as a whole contribute 1. So that is the thing I did. So in a of I of 1, I simply incremented a of I of 1 by 1. Similarly, if this particular bit was 0 for this particular number, so I just kept on traversing till for that particular number I am getting the bit as 0, that is not of v of j and 1 left shift I is true. Keep on simply incrementing my j, and simply incremented the 0th value for this particular index by 1. So this is the code for this, where I am storing for every ith bit how many continuous zeros I have, like how many sets of continuous zeros I have and how many sets of continuous ones I have. The next thing that I constructed is I constructed a vector int visited of size 21, 0. And in this, what I am doing is I have a visited vector of size 21. So this is bit 0, 1, 2, 3, 4, 5. So what we discussed, that we need to keep a check that for what numbers are there which have the same configuration, something like this 1 0 0 1 0 1 0 0 1 0. We need to keep check of that. So in this visited vector, if let's suppose index 0 and index 4, if I is 0th bit and 4th bit have the same configuration for all the numbers, that is for 0th bit also, for if let's suppose there are 4 numbers, so for the 0th bit the configuration is something like this, and for the 4th bit also the configuration is something like this. If this is the case, so I am assigning them the same numbers. So let's suppose I assign them 1 and 1. Similarly, if let's suppose bit 1 and 3 have the same configuration, so assign them one unique value, 2 and 2. Let's suppose 2 have another unique configuration, so I assigned it 3. And let's suppose 5 has another unique configuration, so I assigned it 4. This is something that I am doing for visited vector, which helps me to keep a check that if I am in the ith bit, if let's suppose I am in the 4th bit, so it will help me to keep a check that what all other bits have the same configuration. So how I can do that? For that, I simply iterated from I equals to 20, I greater than equals to 0, I minus minus. If visited of I is not equals to 0, I simply initialized it with 0. So if visited of I is not equals to 0, what does this mean? That this means that this particular bit already has some equal configuration with some earlier bit positions. So for this, I don't need to traverse, because if let's see, if I am at j equals to 20, okay, and let's suppose j index equals to 14, index equals to 12, and index equals to 2 also have the same configuration as that of 20. And let's suppose for 20, I was assigning it value 1. So what I will do? I will assign value 1 to 14 as well, 12 as well, and 2 as well. So if I am done traversing for this, for a particular configuration, so when I come to 14, do I need to traverse again? Do I need to traverse again? The answer is no, because already for this particular configuration, the numbers are assigned. That's not an issue, isn't it? So if visited of I is not equals to 0, that is I have assigned some numbers. So in that case, I am simply continuing. Else, for this ith bit, I am assigning it number 0. I simply initialize my number, number O. I simply initialize my number O with 1. and I am going to all the bits towards the right, that is traversing from I minus 1, j greater than equals to 0, j minus minus, initialized my value of f as 0, and going to each and every number, if for every bit I get the same configuration as that of ith bit, if for every jth bit I get the same configuration as that of ith bit, that thing I am checking. I am going to each and every jth bit and I am checking if that particular bit configuration is equal to the ith bit configuration or not for all the n numbers. Okay. So how I will check? This is something that I am doing. I am going to each and every jth bit, initialized my f as 0, now going to each and every number and just checking that if the ith bit is set, then the jth bit should also be set. Else, if ith bit is not set in that particular number, then jth bit should also not be set. If that is the case, then I am continuing. Else, if this is not the case, so I know that there is at least one number in which the configuration does not match between the bits I and j. So simply marking the value of f as 1 and breaking. If after coming out of this for loop, the value of f is 0, this means that this jth bit configuration matches the ith bit configuration. So in the visited of j, I am assigning the same number o that I assigned to the bit I. And I do this for every bit towards the right. Once I'm done with this, I know that for every configuration, since I need to assign unique numbers, so I simply incremented the value of o. This is something that I did, which helps me to check whether their configurations are same or not. And this is something for storing that what is the minimum number of zero sequence that I have and what is the minimum number of one sequence that I have. Once I am done with this, so now my question comes how to solve. Now I will write the code to actually process the queries. This was actually the pre-computation part. So I first of all calculated the total and value of all the elements in the array. So initialized my R to int max and went to each and every element of the array and did R equals to R and IT. Okay. Now I will process Q queries. So for every query took the value of K and X. Okay. Initialized my F to 0. You will get to know why I'm doing this. Now I am going to each and every bit for a particular query. Going to each and every bit, what I know is that I will be able to turn a particular bit on only when the value of bit I in X is set for that particular bit, isn't it? So I am checking if X and 1 left shift I is greater than 0 or not. If it is, so I initialized my total and value of the array with C, and I am simply checking if the and value is already 1. If the and value is already 1, just tell me, do I need to do any XOR operation with any of the numbers? I will not do, isn't it? Because if I do, so what I have, I already have and values as 1, and I have the number in X in which this particular bit is also 1. So if I do the XOR operation with any of the numbers, the bits will get turned to 0, and the and operation, the final and operation will turn down to 0. That is something that I don't want. So I will not perform any XOR operation and simply output the already have result with me. So I simply output C, mark F as 1 as break. So now you would all be able to relate what does F mean. F mean that we are printing the result. If we are printing some result, so we are marking F as 1 and break. Else for that ith bit, I know that X, the value of X for that ith bit, in X, the ith bit is equals to 1. So I can do some operations and turn that particular bit on for all the numbers in the array. So how will I get that? How many minimum number of operations I need? That I will get by, for the ith bit, what is the minimum number of zero sequence that I had? From that I will get. So I simply took this. Now if the required value is lesser than equals to K, so I know that, yeah, I got a bit that I can turn 0. So I know that since I am following the greedy idea that the first leftmost bit that I get that I can turn 0, I will turn that 0 and just print the answer. But we already observed that when we try to turn that particular bit 0, so accidentally, to our profit, some other bits as well get turned to 1. Where if we try to turn a particular bit 1 in all the numbers, so to our profit, accidentally, some other bits also get turned to 1 that had the same configuration. So what we did is we went to each and every bit individually and just check if the value of x for that particular bit is 1 or not. If it is 1, if it is 1, and the value of c at that particular bit is also 1. Okay, let me discuss this thing. If I, let's suppose, tell you that already I have these bits as 1, I had some configuration, something like this. And what I decided is that at this particular, for x, this particular bit position was 1 and this particular bit position was also 1. So for the final AND value, I was getting 0 over here and 1 over here. And I decided that I want to turn all the bits, this particular bit on in all the numbers. This is something that I decided because greedily, this is something that I am doing. That the leftmost bit, I want the AND value 1 over there. I don't care what the value are there in the right, isn't it? So if I do the AND operation, if I do the XOR operation of these two numbers with this value of x, so just observe this one thing, that since at this particular bit x has value 1, so for these two numbers, these bits will get turned to 0. And once it turns down to 0, I will get the final AND value, which I was getting as 1 in this particular bit position. It will simply turn to 0. So what I am doing is, I am going to each and every bit. If the value of x is 1, and if the value of x is 1 and the value of c is also 1, c is actually the already having AND result of all the numbers. So for that particular bit, if in c also it is turned on, so I know that since I am doing some XOR operations, so what will happen? That particular bit will get turned off in the final result c. So I simply made c as c XOR 1 left shift t. When we do this c XOR 1 left shift t, what will happen? If this particular bit is 1, so this particular bit will get turned off. How to turn a particular bit in bit manipulation? I hope everyone knows it if you are solving this particular question. So if these are the bits and I want to turn this particular bit on, I will simply XOR it with this. I will simply XOR it with this, and this particular bit will get turned off in my final result. So to turn a particular TH bit off, I am simply doing the XOR operation of it with 1 left shift T. If this is not the case, if a particular bit is set in X, but all the values in C are not like 1, that is in the final result of AND value, we are not getting the final result of AND as 1 in that particular bit. But I know that for ith bit, I am going to turn that particular bit on, isn't it? Because required is less than equals to k. So I will look if the configuration for the T8 bit is same as the ith bit or not. That is, visited of I is if it is equal to visited of t. So I know that in the final AND result, accidentally the T8 bit will also get set. So initially it was 0. I need to uh, turn on it. So I need to flip that particular bit in the final AND result. So in the final AND result C, what I will do, I will simply turn it on. So I will simply do C and 1 left shift T. Okay. And we know that the ith bit is getting turned on. The ith bit is getting turned on. So I simply print the AND value that I got or 1 left shift I. Even if you don't write this, simply print C. So ith bit will definitely get turned on because of this result. Because when you come to ith bit, that is when t is equal to I. In that case, you will get that, okay, for x, that particular bit is set and visited of I is definitely equals to visited of I. So this particular bit will automatically get set. So that's not an issue. But I wrote this something like this in the context. You can simply skip this part as well. You can simply print C over here. And once you print the answer, you simply mark F as 1 and break. Because we know that we can perform XOR operation only at one particular bit. We can't do something like that, that we are setting a particular bit and then we go and aim for another bit. Because if we try to do that, so whatever earlier bit we try to set on, they will get turned off. And that is something that I don't want, isn't it? So simply print C, mark F as 1 and break. If after coming out of this for loop, if my value of F is still 0, this means that I will not do any XOR operation with any of the numbers, and whatever AND result I had initially of the array elements, I will simply print that. So in that case, I simply see out R and a new line. So this was actually the code for this question. It was not too easy to crack, but yeah, it was doable if you just organize the things and understand what actually you need to do. I know it may take like 2 to 3 traversals for many of you, to understand what actually we are doing. And if you are not familiar with the concepts of bit manipulation, I would recommend you to skip this question for now and try to learn bit manipulation first and then come again to this particular question. Then the things will get more clear. And if you know bit manipulation and even after that you are not able to understand, try to give a thorough read to this question. Then go through the explanation once more and then try to think and code it down by yourself. Then the things will become more clear because the code is too big and it will take some time for you all to understand what actually we are doing over here. So yeah, that's all from this contest. I hope the session went well. So yeah, thank you everyone.